Hello everyone, good time. I hope you are all fine. Today in the recitation hour, we are going to focus on an example about double reinforced sections, and we will see how we can first analyze this section, find the strength of a double reinforced section, and also we will look at some additional discussions about load combinations, and we will see how we can compare the strength of sections versus the ultimate loading that we have based on different load combinations. The example is shown over here. You can see we have a cantilever beam. We have dead and live loads on the beam. We have also earthquake load as a point load at the end of the cantilever beam, and also the length of the beam is specified at the end. If you take earthquake engineering or seismic design of either steel structures or reinforced concrete structure, you can understand in that courses that when we are talking about earthquake load, we are talking about the types of shakings that are applied to buildings because of seismic loading or because of earthquake ground motion. Such motions are in general in 6 dimensions, but the movements or the typical and common ways of showing earthquake load is horizontal movements or horizontal directions, and also in some situations we might need to look at the vertical movement of ground. In general, vertical movement of ground is not important. Mostly the horizontal shaking is the important factor when we study earthquake loads. But in situations where we have overhang or cantilever beams like this, the vertical shaking of ground is also important, and that's why in situations like this we have to consider earthquake load. The way that we can consider earthquake load depends on the project and also the type of software that we are using and the type of problem that we are solving. But in this specific situation, I decided to consider the earthquake load as a point load at the end of the beam. That's why we have this situation in this example. We have a cantilever beam, dead loads and live loads are specified, and as you can see, dead load is including the self weight of the beam, and earthquake load is the load that we don't know. And the question is asking about finding the maximum earthquake load that can be applied on this beam based on this cross-section. Based on this cross-section information. As you can see, cross-section is shown over here. We have an I section. It is common to use these sections in large and line girders that we have in bridge engineering, specifically for pre-stressed concrete sections. But in this example, I'm using this section for the sake of just analyzing the section and understanding the analysis procedure for a different configuration of reinforced concrete sections. So you can see we have an I flange and I shape section. The flanges at the top and bottom have different width values. At the top we have 18 inches, at the bottom we have 16 inches. Then you can see that we have also both the tensile reinforcement and compression reinforcement. Based on the situation that we have in this building, I believe you know which reinforcement is compression reinforcement and which reinforcement is tensile, right? We have a cantilever beam like this. Loading is shown. and the way beam is going to deflect is like this. So as you can see, for this section, top of the beam will be in tension and bottom of the beam will be in compression. So we are facing negative bending. And we can also say that this reinforcement is tensile reinforcement and this reinforcement is compressive reinforcement. So now we know what is the section. We learned about the geometry of the section. We know that there are two major reinforcement in the section, tensile reinforcement and compressive reinforcement. So this is a double reinforced section. And as I told earlier, the question is asking about finding the maximum earthquake load that can be applied to this section without failure. Dead load and live load are given, and you can see the strength, the properties of material are also given, F prime C and Fy. Length of the beam is also mentioned over here. And what I need to do is to find the maximum earthquake load that can be applied to this beam. The major question that we need to answer is that phi mn should be greater than mu, and this mu is the ultimate moment because of all of these loads, considering the load combinations that we have in the code and in the ultimate strength method, and phi mn is the strength of this double reinforced section. So we have two major things to consider. At first, I have to find mu based on the loading, and then I have to find the strength of the section and compare it versus mu. Initially, I'm going to focus on this double reinforced section, and I'm going to calculate the strength of this section. Finding the strength of the section is not difficult. We talked about it before. As you remember, in the fourth chapter, we talked about the procedure for analyzing double reinforced sections. We talked about this flowchart, and I told you about the steps that we have to follow for analyzing double reinforced sections. The major difference that we have in double reinforced sections versus regular sections is the fact that in these sections, we have to make an assumption about C, or the depth of neutral axis, and based on that, we have to find the depth of compression block and the stress in compression reinforcement. As you can see, we said we have to make this assumption about C, or depth of neutral axis, as an initial guess, and then based on that, we have to work on this, check the equilibrium, and if equilibrium is not completely satisfied, or the accuracy that we are looking for in the force calculation is not achieved, we have to make additional tries in order to reach the accuracy that we want. Over here, you can see the flowchart. I'm going to just follow these steps in analyzing the section and finding the strength of the double reinforced section that we have over here. So the beginning step of the analysis is very similar to what we had for regular reinforced concrete sections. We are going to consider the tensile reinforcement and then the basic assumption that we have for all reinforced concrete material, or reinforced concrete beams. For all of them, we are going to first assume that the tensile reinforcement has yielded at the ultimate strength stage. And that's why I can say tension force is equal to AS Fy. AS is the area of tensile reinforcement. We have two number 14 bars. As you can see, it is specified in the question. We have number 14 bars at the top. So area of each number 14 is equal to 2.25. And then Fy is mentioned as 60,000 PSI, or grade 60 steel is used for reinforcement. So tension is equal to 2 multiplied by 2.25 multiplied by 60,000 and that is 270,000 pounds. Then we have CS, compression force in steel, and that is A prime S multiplied by F prime S, or the compression force in this reinforcement that we have over here is area of steel, area of reinforcement multiplied by the stress. That is the simple equation for finding the force in members. The stress multiplied by area. Area is based on 4 number 6 bars, and the stress, we don't know this. So I'm going to say stress is equal to the Young modulus of steel multiplied by the strain at the level of compression reinforcement. Based on the strain distribution that we have, we can see this is the portion that we are going to focus for compression region. And in this region, you can see we have 2 triangles. One, the smaller one over here, and the other one is the larger one over here. For these triangles, I can use and write the similar triangle ratios. For the smaller one, we can say epsilon prime S over C minus D prime. C minus D prime is this side of the triangle, and as you can see, D prime is the distance from compression reinforcement to the bottommost region, or the extreme compression fiber or compressive fiber of the section. So D prime is shown over here. C minus D prime will be this side of the smaller triangle. So epsilon prime S over C minus D prime is equal to epsilon C, which is 0.003, the maximum compressive strain in concrete, over C. We are looking at the larger triangle. So considering this, we can find the equation for epsilon prime S as a function of C, or depth of neutral axis. So now I can return this epsilon prime S into this equation and multiply it by ES and return it to this equation to find the compression force in steel as a function of C, or depth of neutral axis. So that is the compression force in steel. So far we could find the tension force over here. Now we could find compression force in steel based on C, or depth of neutral axis, which we don't know. And then we have compression force in concrete, or CC, the compression force that we have over here based on this compression block, and that is 0.85 F prime C BA minus A prime S. And this equation is the same equation that we used before for regular sections. The only thing is that I have to subtract or exclude the area that is taken by compression reinforcement. Right? That is the only difference. Now this is the equation for compression force in concrete. And of course, A is the value that we don't know. We don't know the depth of compression block, but we know we have this relationship between A and C. A is equal to beta 1C. So instead of A, I can put C multiplied by beta 1. Right? This way, the compression force in concrete will be also a function of C, depth of neutral axis. And now that everything is a function of C, or depth of neutral axis, I can make the assumption about C and then begin the trial procedure. So far, based on these steps that I specified in the presentation, we passed this step, we calculated the tension force. Now we are over here, based on the forces that we calculated in compressive steel and concrete, we are going to pick a trial value for C, and based on that, we are going to update the compression in concrete by putting that C over here and multiplying it by beta 1, and also putting it over here for finding the compression force in steel, and then checking the equilibrium. So We said for the first try, because at the beginning we have no information about the section and forces, we have to just make an assumption, and it is completely experience based on the experiences that most of the structural designers had. It is better to begin with d over 4 and d over 3, so c should be between these two values in the beginning, and then based on the check that we have at the end of first try, we can get closer to the correct value or accurate value for C. So D is equal to 26 inches in this problem. D is defined from tensile reinforcement to the extreme compression fiber of the section. Excuse me. And 26 over 4 is equal to 6. 26 over 3 is equal to 8 point something. And a value between these two can be 7. So I'm going to pick 7 inches as the initial value for my C. Now I'm going to return this value into this equation and also this equation for find the compression force in steel and concrete. So as you can see, we said the strain in compression reinforcement is equal to this function of C. I'm going to use this equation and put C over here. So 7 minus 2 divided by 7 multiplied by 0.003 is equal to this much strain in compression reinforcement. Now that we have the strain, we can return it to this equation for finding the stress. Strain multiplied by Young modulus is equal to stress. As you can see, this stress is equal to 62,143 psi. There is an important check over here, and that is the comparison of this value versus Fy. As you remember from strength of materials, when we are talking about regular steel, we are talking about this. Let me draw it in a better place. When we are talking about behavior of steel, regular steel, we are talking about this form of behavior like this, and over here we have Fy. As you can see, in the domain of regular loading and ultimate strength of the section, it just reaches Fy and it does not go beyond Fy until the failure and very extreme loads. But for regular design, we always assume Fy is the maximum stress, and beyond that is just failure and yielding. So as you can see, a stress in steel cannot go beyond Fy. That's why when you calculate this stress in steel based on what you assumed as C, we assumed C is 7 inches. Based on that, we looked at a strain distribution and find the strain in a compression reinforcement. And now, based on that strain, I'm calculating the stress and compression force in steel. So now this stress we can see is greater than Fy, which does not make sense based on the behavior of regular steel. So I have to just take Fy as the compressive stress in steel because it cannot go beyond that. So F prime S that we calculated based on the trial value for C was greater than Fy. I took Fy, and now that I know what is F prime S, stress in compression reinforcement, I can multiply it by area of the reinforcement and find compression force in steel. That is done over here. And now we can use this equation for finding the compression force in concrete. So far we could find this one, and now I want to find this one, compression force in concrete. For finding that, we know what is the equation. This is the equation. I have to just use the value of C that we have over here and put it over here for finding A. And then once I find A, I can put it in this equation for finding compression force in concrete. So A is equal to beta 1 by C. As you can see, 0.85 multiplied by 7 is 5.95 inches. It is smaller than 6 inch. As you can see, this is the flange of the section in compression region. If my compression block is greater than this value, I have to consider the compression region of concrete as one portion at the top and also a lower portion at the bottom, because we have different geometry. But if depth of compression block is just lower than the depth of flange, I mean smaller than 6 inches, then the compression in concrete will be just a simple rectangular shape inside the bottom flange. Over here, based on the C that we assumed or guessed at first, A is smaller than 6 inches, which means compression block is just inside the flange. This is the general configuration for a stress distribution. And now that we guessed some value for C, we know that A is actually lower than the depth of the lower flange. So now that I know this is the depth of my compression block, I can use this equation, and B is just the width of the compression flange, which was 16 inches. Use the A that we calculated over here in the equation. A prime S was 4 number 6 bars, so 4 multiplied by area of each number 6 bar, and then calculating the compression force in concrete. Note that all of these values that we calculated so far was based on this initial guess, right? So now that we know the tension force, compression in concrete, and compression of steel, compression force in steel, we can check if the section is in equilibrium or not. We know the section should be in equilibrium, and based on that we can check the accuracy of this initial guess. So I'm going to compare the compression forces. As you can see, I'm adding the compression forces, compression force in steel and concrete, and by adding them, I'm going to compare the value versus the tension force. Adding them together is about 344 kips. Tension force is 270 kips. So as you can see, the compression force is much greater than the tension force, which means in the second try, I have to reduce the value of C. Reducing the value of C means reducing the depth of compression block and also reducing the amount of compression force in concrete and making the total compression closer to the tension force. So I calculated the total compression force. It was greater than the tension force, so I have to reduce C in my second try. Now I have to see if it is necessary to have a second try or not. And that is based on comparison of difference between forces. As you can see, I'm finding the difference between compression forces and the tension force, and I'm comparing it versus 5% of tension force. As you can see, the difference between tension and compression forces is about 74 kips, and that is much greater than 5% of the tension force, which is just 13.5 kips. Now it means that I have to have a second try, and in the second try, I'm going to consider a lower value or a smaller value for C, because compression was greater than tension. So at first, my C was 7 inches. Now, looking at the difference, once you solve examples and become more familiar with the procedure and you get feeling about depth of neutral axis and the forces, you can have your second and third guess very closer to the accurate value, and this way we can minimize the amount of trials that we have for the solution. It is completely experience-based. But if you don't have the experience, it doesn't mean that you cannot solve the problem. It means that you might have one additional try to get closer to that accurate value for C. So now I'm going to make my second try. I learned that I have to reduce the value of C. from 7 inches, I'm going to go to 5 inches. So my second trial value for C is 5 inches. Now I'm going to just repeat the procedure that we have over here. Finding the strain in compression reinforcement. Based on a strain, I'm going to find the stress. Once I have a stress, I multiply it by area to find the force in compression reinforcement. And then once I have that, I have to find the compression force in concrete, finding A, and then putting A in the equation for finding compression force in concrete, and then comparing the compression forces versus tension force and see if the difference is small enough or not. So again, putting that C value in the equation for a strain, you can see the strain this time is equal to 0.0018. Multiplying the strain by Young modulus, we can find the stress in compression reinforcement. That is 52,200 psi. As you can see, this time it is smaller than Fi, so that is fine. I'm going to use this value for the stress in compression reinforcement and multiply it by area for number 6 bars to find the compression force in steel. So that is one compression force. Then I have to use this C value for finding A and putting it in the equation for compression force in concrete. That is happening over here. A is just 0.85 multiplied by 5. That will be definitely smaller than 6 inches. So compression plug in the second try is also in the bottom flange of the section, which makes the solution easier. But putting that in the equation, you can see in the second try, compression force in concrete is about 170 kips. Now, if we compare it with the first try, as you can see, in the first try, compression force in concrete was about 238 kips. Now, by reducing C, it is 170 kips. So, it is working. Now, adding all the compression forces together, this is the value. Now, I have to compare it versus tension force. Tension force was based on ASFY, that is 270 kips. As you can see, this time it is 260. We get much closer in comparison to the previous try to tension force, and it is smaller than the tension force. So it means in my third try, I have to increase C just a little bit. That way A will be increased and compression will be closer to the tension. But that is just the information about third try. I'm not sure, or I don't know yet if I have to have a third try or not. For understanding the necessity of third try, I have to compare the difference between compression and tension forces versus 5% of the tension force. So adding the compression forces, it was the value. Now I'm calculating the difference between this and tension force. It is 9 kips. 5% of the tension force, we calculated it before. That was 13.5 kips. And as you can see, the difference is just 9 kips. So definitely smaller than 5% of the tension force, which means the second guess or the second trial value for C is good enough to be accepted for this analysis. Once this condition is satisfied, we can say we don't need additional tries, and this guess for the value of C is good enough. So C is equal to 5 inches. Based on this C value, we know the compression force in steel, we know the compression force in concrete, and the tension force in steel was calculated based on that main and basic assumption that we always have. Steel or tensile reinforcement has yielded. Now that we know the depth of neutral axis, it's the time to check for our initial assumption. We have to see whether that steel tensile reinforcement has really yielded or not, and see if the section is tension controlled or not. So I have to look at the strain distribution And now look at this triangle at the top and compare it versus the bottom triangle. Epsilon t over d minus c, that will be this side, is equal to 0.003 over c. The same equation that we used before for typical and regular sections. So epsilon t over d minus c is equal to 0.003 over c. C was 5 inches. It was our second trial value and it was accurate enough. So epsilon t based on this value will be 0.013. As you can see, it is much greater than epsilon y. So far, by the examples that you have solved here and there, you know epsilon y is about 0.002. So it is much greater than that, and also much greater than epsilon y plus 0.003. So the section is also tension controlled, and phi is equal to 0.9. So tension reinforcement has yielded, and the section is also tension controlled, which means it is satisfying the requirement from ACI code. So the last step is to just calculate phi mn for analyzing the section. When we had regular sections, we said we just calculate the moment because of tension force about compression force. But for double reinforced sections, since we have two compression forces, as you can see, one in concrete and one in steel, it is more common to calculate the moment because of compression forces about the tension force. The method is the same. The only thing is that now we are calculating the moment because of compression force about the tension force. That's the only difference. So for calculating that, I have to multiply CC by this distance, right? Multiplying this force by this distance that it has to the tension force, and that is, as you can see, d minus d prime, and then multiplying CC, this force, by this distance, which is d minus a over 2. Those are calculated over here. CS multiplied by d minus d prime and CC multiplied by d minus a over 2. Phi is 0.9 because section is tension controlled. CS and CC are the values that we calculated before. As you can see, these are over here. So I'm going to use these values in the equation, and then d minus d prime and d minus a over 2 are based on the geometry of the section, and a is just 0.85 or beta 1 multiplied by c. C was 5 inches, and 0.85 by 5 will be the value of a. Putting everything in the equation, you can see this is the pound inch, and changing it to kip foot, we have 470 kip foot as the ultimate strength, or phi mn, of the double reinforced section. So we could find the strength of this section, and now it's the time to compare phi mn versus mu, right? Because based on this mu, I'm going to calculate the loading, the moment because of the loading, and then it should be smaller than phi mn. It should be smaller than phi mn, and based on that, I can find the maximum earthquake load that we can apply on this beam. So if you look at the ACI code, we had different load combinations, but in this question, we have the gravity loads and earthquake loads. So I just looked at the loads that are based on gravity and earthquake load, and those are mentioned over here. The first two are just based on gravity loads, 1.4 dead and 1.2 dead plus 1.6 live. These are the two famous gravity loads that we used before a lot. The additional load distributions or load combinations that I have over here, number 3 and number 4, are the load combinations that include earthquake load. So one of them is 1.2 dead plus live plus earthquake, and the other one is 0.9 dead plus earthquake. To remind you about the discussion that we had about load combinations and how we should consider the load factors based on the loading that we have, I can go back to the third presentation or third chapter. And as you remember, this is the table that we had over there. This red block is showing the load combinations just because of gravity loads. But now in this example, we have earthquake load, so I'm considering this load combination and also this load combination in my considerations. As you can see, this one says 1.2 dead plus earthquake plus 1 live, and the other one is saying 0.9 dead plus 1 earthquake. And those are used over here, 1.2 dead plus live plus earthquake, and the other one is 0.9 dead plus earthquake. So I am going to calculate mu, the ultimate moment, because of all of these load combinations, and compare it versus phi mn and see what is the situation. If phi mn, if phi mn is smaller than mu, it means the section fails. But if this value is greater than mu, it means section has enough strength to carry the load. If we put them equal to each other and based on that find the load, that will be the maximum load that the section can carry before failure. So let's consider the first situation. The first maximum or the first ultimate moment in this situation or for this load is just based on 1.4 dead. Dead load is the distributed load, and as you can see for a cantilever beam, we know the maximum moment is happening over here, and that is the load multiplied by length squared over 2. That is not difficult. We have a just distributed load, we can just put a concentrated load because of this distributed load, and that is the area under the load that will be at the centroid of the uniform load, and then multiply to the end of the beam, that will be the moment at the end. These are just statics and structural analysis. You are already familiar with this. So maximum moment at the end of the beam because of this distributed dead load that we have, because of this first load combination, is just 1.4 multiplied by the dead load. If I go back to the very beginning of the problem, you can see dead load is given to us as 2 kip per foot, and live load is given to us as 4 kip per foot. So 1.4 multiplied by dead, 1.4 multiplied by the distributed dead load, multiplied by L squared. L is 10 feet, that is given in the question problem, divided by 2. That will be 140 kip foot. Phi mn, as you can see, was equal to 470. So it is smaller than that, which means the section has enough strength to carry the gravity load. And that is the first combination for just gravity load. The second combination for gravity loads is this one, 1.2 dead plus 1.6 live. So 1.2 multiplied by the dead load plus 1.6 multiplied by the live load, and then 10 squared over 8. That will be the moment because of all the gravity loads in the beam, and if you calculate it, it will be 440 kip foot. Phi mn was 470. As you can see, it is very close. So maybe the designer considered this gravity loads and just designed the section for that, and now he or she wants to see if the section, or what is the amount of earthquake load that this section can carry when it is just designed for gravity loads. So as you can see, the strength of the section is just a little above the maximum moment because of the second load combination. So far we were just checking the strength of the section because of gravity loads, and they are all passed. If phi mn was smaller than these, we should say the section is already failing under gravity loads and it has no capacity for earthquake load. So maximum earthquake load is equal to 0 because the section has already failed under gravity loads. So Now let's consider the third load combination, which includes the earthquake load. Now the maximum moment because of the situation of having gravity loads and earthquake load is the maximum moment because of distributed load and also the maximum moment because of a point load. So the equation is like this. WL squared over 2 is the moment because of distributed load, and then point load multiplied by length is the moment because of point load at the end of the beam. Load factors are included based on the load combination 1.2 dead plus 1 live, 1.2 dead plus 1 live, and then load factor for earthquake load is equal to 1. That's why I just put 1 instead of lambda E. So E, earthquake load multiplied by L or 10. That will be the maximum moment at the end of the beam based on this load combination. Right? So considering that will be the equation for E, and as you know, E is not known. That is the whole purpose of the question. We have to find maximum E, and now for finding that, I'm going to put it equal to phi mn. This way we can find the maximum earthquake load that can be applied to the beam based on this load combination. Solving this equation, we can see E max is equal to 14.8 kips. Now I have to consider the last load combination, which is just 0.9 dead and earthquake. It is just based on dead and earthquake load. So I'm going to calculate the moment. This time the distributed load will be just based on 0.9 dead. As you can see, it is over here. And as you can see, the factor for earthquake load is equal to 1. So the moment because of that point load will be just lambda E multiplied by L. The load factor for gamma E, the load factor for earthquake is equal to 1. As you can see, it is 1. We have no load factor, so that is 1. That is why, similar to the previous load factor, that is equal to 1. And L is equal to 10 feet, so that 10 feet is over here. And adding these two moments together, this will be the equation, and it should be equal to phi mn to find the maximum earthquake load. Solving this equation, you can see based on this, maximum earthquake load is equal to 37.8 kips. So based on the gravity load combinations, we could see the section has enough strength for gravity loads. And based on the last two load combinations, we could find two values as the maximum earthquake load. 14.8 kips and 37.8 kips. Which one should be the value to finally specify as the maximum possible earthquake load on this beam? Looking at these two values, that is definitely 14.8 kips, right? Because if I say the maximum earthquake load is 37.8 kips, then if I put that value in the third load combination, the moment will be greater than phi mn and the beam will fail. That is a very interesting point, and that is majorly based on the understanding that we have about load combinations. So this value will be the maximum earthquake load that I can apply on the beam, and if the earthquake load is this much or lower than this, the beam can carry this load safely. This is how we can solve this question. I believe it was a very interesting question for both understanding the concept behind load combinations and load factors and how these will result in section analysis, and also a good example for looking at double reinforced sections and seeing how to, or learning how to analyze them. One thing that you can do as some practice at home would be to just remove the compression reinforcement and solve the problem again by just considering the tensile reinforcement. This way you can see removal of compression reinforcement, how we'll change the strength of the section, and then you can see, or you can work again on the load combinations and see the maximum earthquake load. One thing that is good to notice and also mention when you are working outside on consultant companies is that usually they don't include compression reinforcement in a strength analysis. They just ignore it and find the strength of the section based on tensile reinforcement. It will simplify the procedure. Clearly, you can see how it simplifies it, but in terms of the difference that we have in the strength of the section when ignoring the compression reinforcement is something good to be studied, and you can work on it or kind of check it by solving this example again. Solve the same problem, just remove the compression reinforcement and see what is phi mn and compare it versus mu. So this is the example that we have about double reinforced section. Please solve it again at home. If you have any question, just let me know. We can definitely discuss it in a meeting, in a WebEx meeting, or through email. Thank you.